Hello everybody, and welcome to our second real analysis lecture. We're going to assume some things that are not directly in evidence. Last time we proved that the sum of two rational numbers is rational. We did that in class. And for homework, we have to prove that the difference of two rational numbers is a rational number. Also for homework, we have these two assigned. And the instructions are prove or disprove. So they may be true, they may not. If they're true, prove them. If they're false, give a counterexample. The first proposition is the product of two rational numbers is a rational number. And the second proposition is the quotient of two rational numbers is a rational number. And again, the instructions on these two are, if they're true, prove them. If they're false, provide a counterexample that shows that they're false. And we will assume in the lecture that I'm about to give that we know the results of these propositions. So if it's true, for example, that the product of two rational numbers is rational, we may use that in our proof of whatever we do today on this video. Here's our first, Here's our first proof for today, our first theorem. The sum or difference of a rational number and an irrational number is irrational. And for the sake of making this proof a little bit more straightforward, I'm going to take this statement and write it explicitly as a conditional statement. So let x be a rational number, and let y be an irrational number. Or I'll tell you what, I did say I want this in the form of a conditional, right? So if x is a rational number and y is an irrational number, then x plus or minus y is an irrational number. Okay. And let's identify our hypothesis. Here's our hypothesis. And here's our conclusion. So this is actually what we're going to prove. If x is a rational number and y is an irrational number, then x plus or minus y is an irrational number. And we will prove only that x plus y is an irrational number the case involving x minus y being an irrational number. Or you know what? Instead of saying the case, let me say the proof involving x minus y being an irrational number. Is analogous. Same proof, we just replace the plus sign with a minus sign. That's pretty much it. So we're only going to show this case, but this case is pretty much the same except we replace the plus sign over there with a minus sign here and carry it through the proof. Okay. Now, you know how I am. I don't know how to do any of these proofs. I have no idea how to do this. So here's what I'm going to do. Just to give myself some momentum and to get the proof started, I'm going to let the hypothesis be given. And just so that I know exactly what it is that I'm assuming, I'm going to write out the hypothesis. Suppose that x is a rational number and that y is an irrational number. Okay. So I've written out my hypothesis explicitly. I know since x is rational, I can write it as the quotient of two integers where the denominator is not 0. I can't do that for y. And furthermore, I don't really know too much about why does, what it does look like. It's irrational. There's no very nice, concise characterization of the appearance of a rational number, of an irrational number, the same way that there is a rational number. X is rational, it's the quotient of two integers, denominator non-zero. Y is irrational. Well, what does it look like? We don't have any tidy characterization for an irrational number. So now I've written my hypothesis down and I still don't know what to do. I haven't got a clue what to do next. And since I really don't know what to do next, I'll hit the chicken switch. I'll change my tactic and I'll do this proof by contradiction because I can't think of anything else to do. So I'll try doing a proof by contradiction. And oftentimes, after we've written down our hypotheses and we still can't seem to get anywhere, when we don't know what to do, it may be a good idea to try doing a proof by contradiction. So let's do that here. And I'll say this. Suppose for the sake of deriving a contradiction, okay, we're doing a proof by contradiction, so what is it that we're going to suppose? We're going to suppose that the conclusion that we want to arrive at is false. We're going to assume that this conclusion is false. And that somehow is going to give us a contradiction. Specifically, this is what we're going to assume is false. X plus y is an irrational number. So the negation of this, x plus y is irrational, is x plus y is rational. We're assuming exactly the opposite of what we want to prove. We're assuming the negation of what it is that we want to prove. And that's what we do in a contradiction proof. We assume the negation of what it is that we want to prove. So we're assuming that x plus y is rational. And I still don't know what to do. So I'll give this real number a name. As a matter of fact, I'm assuming more than that this is a real number. I'm assuming that this is rational, isn't it? So if I'm assuming that x plus y is rational, then there has to be some rational number z, for example, such that x plus y equals z. That's what I'm going to show, or assume rather. So this implies that there exists a rational number z such that x plus y equals z. Okay, I'm back. I just wanted to clear up the board and give us some more space to work with. But this is where we ended up. That we said that if the sum of x plus y is rational, then there has to be some rational number z such that x plus y equals z. And I think I'm kind of getting the picture of how this proof has to go now. Here's x, and x is a member of the rationals. Here's y, and y is a member of the irrationals. And here's z. Z is a member of the rationals. Whoops. Z is a member of the rationals. Z is a rational number, a rational number. And now all of a sudden, the wheels are turning. I can pretty much see how this is supposed to go. And remember, with a contradiction proof, we want something to go horribly wrong. We want the you-know-what to hit the fan, so to speak. And looking at how I have this equation diagrammed, I can see how things are going to go horribly wrong in just a second. All I have to do is rewrite this equation. Whoops. Let's see. I want y by itself. Okay. There we go. And we're going to label this again. Y is an irrational number. Z is a rational number, as is x. Now, does something look wrong with this picture? Take a look at it. This tells us that y is rational. Why? Why is y a rational number? Because y equals the difference of two rational numbers, and we know that that's rational. Y is rational because y is the difference of two rational numbers, x and y. Did something just go horribly wrong? You bet it did. Here we've established that y is rational, but by hypothesis, y is an irrational number. This is exactly the horrible thing that we wanted to happen. Yep, it contradicts our hypothesis. By hypothesis, y is irrational. So let's just sum it up for our reader. Technically, we're done with our proof, but let's just summarize what we're done, so in case any of our readers are on autopilot, they'll realize we've actually done what we set out to do in this proof. And so we spell it out for our reader. We say, since the assumption that x plus y is a rational number leads to a contradiction, the assumption must be false. And this is something we probably should do for our reader just to make sure they get the point. We got a contradiction, but now we have to go back and see what it is that caused the contradiction. Just like when a plane crashes, the FAA doesn't just say, oh, well, the plane crashed. When a plane crashes, they send a team of investigators out to collect all the evidence they can, reassemble as much of the plane as they can so that they can find out why the plane crashed. When we get a proof by contradiction, we want to make sure we understand why we got the contradiction. What was it that caused the contradiction? And in this case, the thing that caused the contradiction was the assumption that x plus y is a rational number. That's what causes the contradiction. So this assumption must be false. Well, if the assumption that x plus y is rational must be false, then the negation of that must be true. So the sum of a rational number x plus an irrational number y is irrational. And that's what we set out to prove in the first place. Okay, now that we've shown that the sum or difference of a rational and an irrational number is irrational, the next thing we'll have to do is prove or disprove that the product or quotient of a rational number and an irrational number is irrational. And this is a homework exercise. I'll tell you when it's due in class. I'll give you the assignment formally by Canvas and tell you the due date and so forth and so on. But this is something that may or may not be true, and we won't do it in class, at least not right away. It's going to be a homework exercise. The next thing that we are going to do in class is something that may seem a bit surprising at first, but when we think about it a little bit, maybe not so surprising after all. Here's an interesting fact. The sum or difference of two irrational numbers may be irrational or may not be irrational. If we take two irrational numbers, I'll tell you what, if we put a blindfold on, and when we're blindfolded, we stick our hand into this bag containing irrational numbers, and we pull two irrational numbers out of the bag, any two, the sum of those two irrational numbers could be rational, or the sum of those two irrational numbers could be, the sum of those two irrational numbers could be irrational, or the sum of those two irrational numbers could be rational. It depends on the two irrational numbers that we randomly pull out of the bag. So let's see. Let's see what it is I'm really trying to prove here. Let's do rational first. There exist two irrational numbers, x and y, such that their sum is rational. Also, there exist, and we won't call it x and y, we'll call it p and q, I guess, two irrational numbers such that p plus q is irrational. So that's really what this is about. The sum or difference of two irrational numbers may be irrational or may not be irrational. In other words, we can find, or there exist, two irrational numbers such that their sum is rational. There exist two irrational numbers such that their sum is irrational. So let's look at this one first. There exist x and y that are irrational such that their sum is rational. Okay. Well, I'm going to pick the easiest case that I can. Let x be the square root of 2, and let y equal... How do I make this as easy as I can? X is the square root of 2, and I want to get an irrational number y that I can add to x and for sure have a rational number. What should y be? What would be the easiest, sneakiest, low-down trick we can pull here? Maybe make y equal to negative square root of 2. X and y are irrational. And x plus y is equal to square root of 2 plus minus square root of 2, which equals 0. Yep, there we have it. This is a rational number, and yet these two guys are both irrational numbers. So we do have the sum of two irrational numbers yielding the sum of two irrational numbers yielding a rational number. Now you might look at that and say, oh, that was a dirty trick. That's a special case. Well, it was a dirty trick. It was a sneaky trick. But you know what? In math, sometimes we like these. We really, really, really like these. So remember this. This is a nice example. Sometimes when we prove something, the easier and the simpler it is, the better. And this is one of those cases. But let's use a different x and y, both of whom will be irrational, but their sum will be rational. So we'll do another example. This time it won't be quite such a sneaky trick. And this is actually what we might call a construction proof. We're going to have to construct our x and our y. We're going to have x and y both being irrational numbers, but their sum is going to turn out to be rational. And we're not going to use the old y is the negative of x trick and we add them together and we're going to get 0. We're going to do something a little bit different. What do we know about irrational numbers? You know? I haven't mentioned this yet. Oh my goodness. Shame on me for not mentioning this earlier. I defined a real number, and I said a real number is a number on the x-axis. I also said alternatively, a real number is any number that has a decimal representation. whether that representation is terminating, or whether it's non-terminating repeating, or whether it's non-terminating non-repeating. Any number that has a decimal representation is a real number. Well, you know, I'm going to put this fact in evidence. And since we're on the pod system and we might have some time to do this semester, we may actually prove this. But for right now, I'm going to let it be given. A real number x is rational exactly when its decimal representation is either terminating or non-terminating repeating. So any real number that has a terminating decimal representation, it's rational. Any real number that has a non-terminating but repeating decimal representation is rational. So what does that leave? Yeah, by the way, we may prove this in this class. We may have the time to do it. All irrational numbers are characterized by the fact that they have a non-terminating, non-repeating decimal representation. Now, maybe I should spell it out differently. A real number x is irrational if and only if x has a non-terminating, non-repeating decimal representation. And a real number can't have both a non-terminating, non-repeating decimal representation and a non-terminating, repeating decimal representation. Can't have it both ways. If a decimal is non-terminating, if the decimal representation is non-terminating, it's either got to be non-repeating or it's got to be repeating. No number can fall into both categories. So either a real number is in this category or it's in this category. And X is irrational exactly when it has a non-terminating, non-repeating decimal representation. Okay. Now let's get back to this other example that I was going to use to show that the sum or difference of irrational numbers can be rational. We're going to create two irrational numbers, x and y, whose sum is going to be a rational number. Now, what do we know about irrational numbers? They have a non-terminating, non-repeating decimal representation. So could we create an x with a non-terminating, non-repeating decimal representation, and then create y with a non-repeating, non-terminating decimal representation, such that when we add them together, we get a non-terminating, repeating decimal representation? Let me write down what would be a good choice for x. I'll say x is 0.10, 1110, 1110, 11110, and here's the pattern. This does not repeat. There's no portion of this decimal representation that occurs over and over and over again. But we have 1 1 and a 0, then 2 1s and a 0, then 3 1s and a 0, and 4 1s and a 0. After each 0, we have one more 1 than we had previously. This is non-terminating and it's non-repeating. Now, how could I define a non-terminating, non-repeating representation for y that would be such that when I add these two things together, I get a non-terminating, repeating decimal? Can you think of how I would have to define y? And if you're guessing, well, every place up here that we see a 1, put a 0. And every place up here that we see a 0, put a 1. You're absolutely right. 0 1, 0 0 1, 0 0 0 1, 0 0 0 0 1. After each 1, we have one more 0 than we had prior. So after this one, we have 2 zeros. After this one, we have 3 zeros, and so forth. Oh my goodness. And what happens when we add x plus y? We get 0.10. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. This is rational because it's non-terminating it's non-terminating, but it's repeating. This digit, this string of length 1, just keeps repeating infinitely. It's a non-terminating but repeating decimal. So here we'll note x and y are irrational because they are non-terminating, non-repeating, but x plus y is rational because it's non-terminating, repeating. So we actually gave 2 examples of irrational numbers whose sum was a rational number. And now down here I'll put the case involving the difference of irrational numbers. Is analogous. As a matter of fact, what we could do is say, okay, let x be square root of 2, let y be square root of 2, x minus y is 0. There we have it. Or, if we used a construction proof like this, and we wanted to show that the difference of 2 irrational numbers was irrational, just put a negative sign here, negative sign, and then x minus y would be x minus this thing, and we'd still get a rational number. So yes, the case involving the difference of 2 rational numbers is analogous. Now, do I have time to do the second half of this proof? The sum or difference of 2 irrational numbers could be irrational. I just thought of a quick one. How to get the sum of 2 irrational numbers to be another irrational number. We'll use the same x that we used before, but now we'll let y be the same thing. And I'll say, observe, x and y are irrational because they are non-terminating, non-repeating, and oh, look what happens when we add x and y together. 0.2022, 0222, 02222, Ah. So this is, see, x plus y is, see, x plus y is a member of the irrationals because it is non-terminating, non-repeating. Okay, so we have the sum of two irrational numbers that turns out to be an irrational number. Let's see, do I have time for one more quick one? I think so. Another example. Okay. X and Y are well-known irrational numbers. X plus Y equals square root of 2 plus square root of 2, which equals 2 square root of 2. Now, for homework, you're supposed to show, prove, or disprove that the product of a rational number, what the heck. I'll let this one out of the bag, just for the sake of brevity. This is irrational, as it is the product of a non-zero rational and an irrational. Hence, it is irrational. So we have x, which is irrational, y, which is irrational, and x plus y is irrational. So this is another example that shows that the sum of two irrational numbers can be an irrational number. So if we add two irrational numbers together, we don't know what we're going to get. Could be rational, could be irrational, we don't know. Gotta go.